The first lecture of today is dealing with transaction costs. More specifically, we're going to look into how we add now transaction costs into the Markowitz model that you were introduced to the last couple of weeks, right? So the idea with transaction costs is that you can have some linearly proportional transaction costs, or we can just call them linear transaction costs. It's normally just a percentage of what you invest, you will pay in transaction costs, or the percentage of what you buy or sell. Or you can have fixed transaction costs. So no matter how much you buy or sell, you pay, let's say, 50 Danish kroner for a single transaction, right? So these are the two kinds of transaction costs that we're going to look at today. And I'm going to show you how you can model this first in algebra and then into GAMS, which is essentially what you are going to do, but that's based on the algebra I'm going to explain here. Right. So the form for these two transaction costs is that we have, let's say you go to an exchange and you want to invest, let's say 100,000 krona in some stocks, right? And what you find out, you want to know what are the costs of investing this 100,000 krona in a number of stocks, let's say. And then they have written something to the effect of that you will pay 0.1% of the amount you're investing. That would be that's the transaction cost, right? So that's what we call a linear transaction cost. But you have to pay a minimum of, let's say, 50 krona, right? So whatever number is smaller, either 0.1% of what you buy, or 50 krona, right? And that could be shown in a function like that. So C0 in this graph is your fixed transaction cost. So no matter, as soon as you buy a little bit, or sell for that matter, then you have to pay C0 as the transaction cost, right? And then at some point, the variable transaction cost will be more than this fixed cost. So if it was, let's just take the example, and you can help me with that. So let's just put some numbers on that. Like the example I gave you, let's say you can trade, you want to buy 100,000 krona worth of, let's just to make it simple, just one stock, right? But I tell you this is 50 krona, that's your fixed cost. So that's my total cost. And in this one, this is my X, let's say how much I buy. So what is the break-even point? So how much do I have to buy before I don't care whether I pay the 50 krona or 0.1% of the amount I have just bought? So it's kind of simple algebra. How much? 5,000. It was 0.1%. So it's 50,000, right? So 50,000, which is here. So up to 50,000, I'll be paying exactly, if I buy for 1 krona or 0.1 krona, I'll still pay 50 krona, right? So it's not a very good idea to buy much less than 50,000 krona then, if that was the cost structure, right? Because if I buy 10,000 krona, then, 50 krona of that would be, a 0.5% transaction cost, which is relatively high, right? 1,000 krona, definitely a bad idea, and I'm paying 5% transaction cost for, so in this particular platform, then, if the fixed cost is 50 krona for one transaction, doesn't sound of much, but if you are buying all the time in and out with the small amounts, then you're betting against yourself, right? So because you have to go and earn more than, let's say, 5% in financial markets in average to beat just the 5% transaction cost you are paying in this market if you're buying 1,000, right? So you have to, of course, be careful about those things, especially when you do with the smaller transactions, or find platforms that do not incur any fixed transaction costs. There are some which don't, but actually there are many platforms which have some sort of fixed transaction costs, which might not sound of much. Maybe it's a couple of dollars or $10, but still, you have to make sure that your trades are larger than a certain amount. And what we are going to do with the Markovitch model, we are going to explicitly put this into the model. So the model will find out if the optimal portfolio is optimal after the transaction costs are accounted for, right? So that's kind of the idea of this lecture, right? So for this example, again, up to 50,000, I'll pay 50. And at this particular point, I can either pay the 0.1% or 0.001, right, which is 0.1%. 0.001 times 50,000, that would be exactly 50, right? And from then on, I'll just pay the variable transaction cost, right? So what I notice here, I say that note that X bar and C0 should be normalized first. So this is, by that I mean, so what is X bar? X bar is this thing, 50,000 over here. And this is our C0, right? So remember that in the Markovitch model we were working with, we had this constraint which says sum of all x's is equal 1. So 1 representing 100% of the portfolio, right? And obviously here, I'm not buying 1 krona. I might be buying 100,000 krona in this case, right? So if I was buying 100,000 krona, there's two ways you could do it. Either you could just go and say sum of x's then is not equal 1, is equal 100,000 krona, which is perfectly fine. You can do that. But if you want to keep to the original model and just use that as it is, using sum of x equal 1, then what you have to do, obviously, is that you have to normalize these numbers so that we play as if we are buying for 1 krona, right? So what does it mean? So this is in terms of 1 krona. So this number has to be, if my total budget is 100,000 krona, so then this number would be then 50 divided by 100,000, right? So it's a relatively small number compared to that. And then you have, for this one, the 50,000 is about the same thing again, right? So this would be, that would be 0.5, right? So that's normalization, right? So these two numbers, and then you can go back and use the original model. Right, so that was, that's the idea of what we're going to do for the next 10 minutes or so. Now let's have a look at how the model, how the algebra would look like for this. And notice here, what I'm showing you here is the first term of the Markovitch model. So again, now we have the constraint sum of x is equal 1. And what was the plain vanilla Markovitch? We had two terms in the objective function. I was maximizing 1 minus lambda. What was the first term? Anybody? Yeah? The return, which was this, you have the mu I times xi, right? So that's the average return, expected return of the portfolio. And then I had a negative here, lambda, and what was the second term? The risk, right? Which is, there's a double sum. So sum over I and j, and then I had here I have xi times qij times xj, right? So this is my first term. Over there I call this return, or R, of x and mu, right? So this is this term in particular that I'm now changing in order to account for the transaction cost, right? Only looking into this term, which was sum of mu I xi. So essentially what that means is that if you take that term, which now becomes into two terms itself, so the return term, the expected return term, has two terms in its own, and then you will replace the single expression here with those two terms, right? Then you have entered the transaction cost into the model, and then you need also a couple of constraints which are down there. Right, so let's go back to the slide and see, so what do they actually say? And let's start with a little bit of preparation before getting there. Because the usual trick for looking into transaction costs, fixed transaction costs, is that you look into the amount you're buying, like we're doing over here, and you're looking into this area. So from 0 up to the level, to the X bar, in which the fixed transaction cost is applicable, right? So for the first amount, that is what we call X0. So this area is X0i. So whatever which falls below X bar, we want to save that in this variable called X0. And anything in excess of that would be X1, right? So the first thing I'm doing, here I'm saying that, well, I want to decompose X, which is how much I'm buying. So my Xi is equal now Xi0 plus Xi1, right? The part applicable to the one cost and the part applicable to the variable cost. Right. And now I want to make sure that whenever I am buying something, first I fill up X0, and then after that's filled up, then I want to fill up X1. That's also why sometimes people would refer to these variables as bucket variables. So just imagine you have a smaller bucket into a bigger bucket, right? And you start pouring water into the smaller bucket. And then only after the smaller bucket is filled up, then the larger bucket starts filling up, right? So that's why they call them bucket variables. X0 is the smaller bucket in that sense, and X1 is the larger bucket. And you want to make sure that the algebra you have, the inequalities that I'm going to introduce you to in a second, they're going to make sure that together with the objective function, they're going to make sure that you get the first bucket filled up first and the second bucket afterwards. Right. So what do they say? The first one essentially says X0 is less than X bar Z. So let's start it here. Xi0 less than X bar. And now let's say instead of X bar, I just want to put the value 0.5 for this example. And Zi, this guy is a binary variable. So a binary variable can have the values 0 or 1, right? So it's either 0 or 1. It can't have any other values. And by introducing a binary variable, by the way, if you remember from the solver statements that I talked about last week, now we will enter into the area of mixed integer programming. So that's also a point on its own, because we have a nonlinear Markovitch is a nonlinear model. Now we are entering a 0-1 variable, so it becomes a 0-1 nonlinear problem. But last week you worked with also the mixed integer quadratic constraint programming, MIQCP instead of MINLP, and you can continue working with that. Still, we are in the realm of MIQCP here when we enter this into the Markovitch model. Right. So what does this mean then? X0 less than 0.5 Z. If X0 is positive, let's say this is 0.1, meaning 10% of the 10% of my money goes into buying asset I. What happens then with Z? Z has to be 1, right? So it can't be 0 because then it's not true, right? So the only thing essentially this one simply does is that if you, as soon as you buy and put some money into X0, then Z would be positive, right? And the other one essentially does the same thing. So I have Xi1 less equal Z, and then I don't have a limit for that because I can just put anything on top. Here, by the way, I have a limit. So I don't want to fill in more than 50% of the money into the first bucket because this is the maximum size of my bucket. I can have less than 50% into this bucket, but anything on top of it, I want in X1, right? Notice here, even though this was, let's say, if this was 0 and this was 0.1, what should Zi still be? 1 or 0? It's a 50-50 chance. But notice this is the same Z over here. So I say xi0 is 0.1, but xi1 is 0. So I'm just buying 10%. I'm filling up the first bucket, but the second bucket is not filled. But what happens with it's the same z, which is over here, which is also, it would be 1, right? So because of this guy, because of the xi0 is equal 0.1, I get a 1 here, and this becomes automatically 1. But it's still fine, because 0 is still less equal 1, right? So that would be fulfilled. But at the second, let's say if I don't have 0.1 here, I can have the maximum, 0.5, which is exactly less than 0.5 multiplied by 1. So this is still true, right? Or this would be exactly binding then. And then this guy, let's say, becomes 0.1, which is still less than 1. So this is going to make sure that this one is going to make sure that I don't fill in more than 0.5 in the bucket. And at the same time, I'm going to have z equal 1, which will also be fulfilled for this. Now, ask you the opposite questions. Can it be that if I did the opposite? Let's say I don't want to put this 0.5 here, and then I put 0.1 here. Let's say I want to do something else. I want to say xi1 less equals zi. So I'll put all the money here, and that would be, then I put a 1 in here, right? So that's still true, right? So I could, theoretically, the model could put all the money in the bigger bucket, rather than pulling the water first in the smaller bucket. You can start with the bigger bucket, right? And then let xi0, which is the other one, be 0, and less than 0.5 zi, right? And this guy would be 1, but doesn't matter. 0 is still less equal 1, right? There's nothing wrong with that, right? So essentially, that could happen. But in a minute, I want you to think, when I go through the objective function, to think why this would not be a good idea, which is why the solver would not do it, right? So, but these two equations, the only thing they ensure is that as soon as you pull some water or put some money either into x0 or x1, the z would be 1, right? No matter which one of them you fill in, z becomes 1. That's kind of the main thing. The other thing is you don't want to allow more than 50% or x bar % of your money in the smaller bucket, right? Now, let's look at the objective function, because what's happening there, I said that the expected return, which was this term, now is turning into two terms. The first one, the first sum over I, it says mu I xi 0 minus c0 z zi. And notice C0 was my fixed cost, so that was my 50 krona, or in 0.0005 krona. As soon as z is equal 1, right? So as soon as I am buying something, that says that I have to pay 50 krona, right? Because here we established the second I'll pay a little bit into one of these buckets, then z becomes 1. And when z becomes 1, it costs 50 krona, right? So that what the first equation says is that mu I xi is how much return you get from putting the money in the first bucket, right? Up to, in this case, up to 50,000 krona. And mu is still the expected return. But now you just have to deduct 50 krona from that, right? That's the first term, takes care of your fixed transaction cost. The second term is for everything in excess of that, which says, well, any money left, which is for x1 I, now it doesn't have a return of mu I, which was its expected return, but it's mu I minus whatever linear cost. So if it was, in average it gets 3%, and the linear cost is 0.1%, then the return after cost is 2.9%, right? Another question for you: why is it that it's not a good idea to fill in everything in x1? And why is it that it's a better idea, it's optimal behavior for this model to put the money first in the smaller bucket and then in the bigger bucket? Can you say that from those two terms in the objective function? 1 here.
Maybe because if you have a positive number amount as the x1, you have an extra negative, how can I say? It's c1 multiplied with xi1, which is something negative for the
Yes,
function.
that's correct. So,
when the x1 is bigger, as you augment the x1, then you have a much bigger negative term.
yeah, but let's say if I only buy in this example, you know, we just established that if I buy 1,000 krona, I still have to pay 50, right? So if I buy 1,000 krona and I put this into the 1,000 krona, instead of putting it into x0, I put it into x1, right? So for that, I only pay, then I pay C1, that's right. I pay 0.1% of 1,000 krona, which is like, what is it, 10 krona, right? Instead of paying 50, right? So why is it that that wouldn't happen? Can't I get away by paying only 10?
No, because the second variable cost activates the controlling binary variable.
Right.
So you will always have to pay the fixed cost.
Exactly. I think you also got it right, but it's just as So that's exactly the case. That what you have here. That was the exact point from this description over here. That no matter if I fill in the first bucket or second bucket, the z becomes 1. So even if, you know, I was trying to cheat and put the money into the second bucket, which is my x1, right? Then I not only pay for that 1,000 krona, I pay 0.1% of that, so I pay 10 krona for that. But then because z is 1, I still get deduced this 50 krona. So then instead of paying 50, I'll pay 60. So still not a good idea, right? So because of that, it's then a good idea to minimize costs. The model will make sure, the objective function will make sure that the smaller bucket gets filled up first, because there is no way, as soon as you start trading, you have to pay the fixed costs anyway, so you can just as well fill up that bucket, and after that is filled, then you can start paying the extra costs, right? So that's kind of how the working of this model is. So what is important here is for you, some of you probably, if you had the 3-week course in mathematical modeling with using GAMS, you're familiar with these kinds of tricks, but if those of you who didn't have it, probably this kind of thinking is new for you. Many times is, you know, the individual equations are simple, but then you have to get them to work together with objective function, with the direction that you're optimizing, maximizing, minimizing, together with something in your algebra, in your inequalities and equations that get the model to work. Right? So that was the part on transaction cost. Any questions on that? Or it was crystal clear? Seems that's good. So there's one assignment on that. So you should make sure that you understand. There's one question actually. Yeah.
Do we see in the diagram the variable z or not?
Well, not the z is here. This is the description of how the structure of the cost is. So, but in order to model that with algebra, you need the variable z, but you don't specifically see it. Z essentially will tell you if you start filling in money either here or there. Okay. Yeah. Any other questions? Otherwise, once you're working with the assignment and GAMS there, we can talk about this again. All right.